I'm not sure.
Right, welcome back. As our final speaker of today's session, we have Yihui, who will tell us about learning stabilizers with noise. Please take it away.
Hi, everyone. My name is Yihui. I'm currently a postdoc at MIT, and the title of this talk is Learning Stabilizers with Noise. Now, there are three keywords there: learning, stabilizers, and noise. And I have published on each of these three topics. But when you put them all together, somehow you get a crypto paper, which is new to me. So this is my first foray into crypto. And yeah, something that's really exciting about this foray into crypto is that it really combines many of these topics that I've been working on before, and hopefully is one way for crypto to also talk to these other areas of quantum info. So this work is at the confluence of two questions. The first is, where does computational hardness arise naturally in a quantum world? And of course, everyone here will have their own definition of natural, but when I say natural, I really want an instantiation of computational hardness in a quantum world that is as common as, say, learning parities with noise is in the classical world. And in fact, the whole thrust of this work is to define a quantum analog of learning parities with noise. So our candidate for computational hardness is decoding random stabilizer states. So random stabilizer states do arise quite a lot in various applications. They appear in quantum authentication schemes, capacity theorems, entanglement distillation, models of Hawking radiation. And so random stabilizer codes are really everywhere. So to give some background, let me first introduce the problem of learning parities, which is one of two building blocks of a lot of modern crypto. So learning parities is the problem where you are given an n by k binary matrix A and a k by, a length k vector y, which is promised to be the inner product of A with a secret vector x. And what you're supposed to do is based on seeing y, you're supposed to infer what the secret was. So the algorithm for this is fairly simple. Does anyone know what it is? Yeah, it's Gaussian elimination. So it's like, this is very efficient, right? So this can be done in basically polynomial in the length of k, time, as well as samples. And here, when I say samples, I mean the number of rows of A. So there's a twist to this problem, which is what happens when you add noise. So when I say add noise, I mean, what if I independently corrupt each bit of y with some bit flip noise with parameter mu? And this is no longer efficient. And the inefficiency of this is quite a marvel. And it's indeed the basis of a lot of modern crypto. So it's no longer efficient in time, in the sense that any algorithm that tries to solve this problem has to run for a very long time. But it could still be efficient in the number of samples, which is the number of rows of A you need to see in order to solve the problem. So we assume that any solver for this can ask for as many rows of A as it wants. So how hard is this problem? Well, the reason this problem is kind of the basis of, or one of the building blocks of modern crypto is because many people have tried for many years to solve it and they have all failed. So one of the earliest attempts was this BKW algorithm, which used 2 to the k over log k time and samples. But here we really see that there's kind of like a balancing act between the runtime of a solver and the number of samples it needs to see. So in 2005, there was an algorithm that significantly decreased the number of samples almost to linear, but yet the runtime then goes up to 2 to the k over log k. And in fact, even before that, it was shown that this problem can be solved with linear in k samples, but then the runtime goes to exponential in k. So the fact that this problem can be solved with almost linear number of samples shows that this problem is information theoretically tractable, and the difficulty of this problem really lies in the runtime. So computationally, it doesn't seem like we know how to solve this efficiently. And this is also true quantumly. And in fact, it was a big deal when 1 or 2 years ago, someone tried to use a quantum. Someone claimed to develop a quantum algorithm to solve LWE, but which is a close cousin of LPN. But then a bug was discovered. So the hardness of these two problems still stands. So yeah, so one of our starting points was to try and formulate a quantum analog of LPN. So the intuition here is that you can roughly think of classical parities as being contained within the set of stabilizer states. And one of the papers that makes this point kind of succinctly is that, so this is a paper that I wrote a couple of years ago where you can actually encode, you can actually use the computational basis output distributions of measuring stabilizer states to encode the problem of learning parities. And that is the circuit that you would use to do it. It's a very simple circuit. And in fact, if you add just one T-gate to this circuit, then it can encode the problem of learning parities with noise. So the T-gate kind of acts as noise. And this has not only been observed by us, but also by GK21, who observed that if you don't use the T-gate to add noise, but you instead consider some form of classification noise on the output, then that also can encode the problem of learning parities with noise. So there's kind of like heuristically a close relation between parities and stabilizer states. So now I'm going to talk about a seemingly orthogonal notion of error correcting codes, but we'll see how it's linked later. So in fact, another view of learning parities with noise is that it can also be seen as the problem of decoding a random linear code. So recall that LPN is the problem of recovering this blue secret X given A and Y. And here you can think of Y. You can think of A as being the generator matrix of some classical code, and Y as being the code word, but with the errors. So that's where the errors are like the noise, the bit flip noise. And so, given this interpretation, it seems natural to approach this problem of quantizing LPN by looking at the problem of decoding quantum error correction codes. So what are the canonical quantum codes? Well, they are stabilizer codes, and here's like a very short introduction to stabilizer codes. So you can think, so stabilizer codes are defined based on stabilizer groups, which are subgroups of the n-qubit Pauli group. And a code can be identified by its stabilizer group. So what's a stabilizer group? It's a group that's generated by n minus k commuting Paulis within Pn. So the code space is the space of vectors that are the simultaneous +1 eigenstate of all the Paulis in the stabilizer group. And if there are n minus k Paulis, then the dimension of the code space is 2 to the k. So you can think of a dictionary, the following dictionary from classical to quantum error correction codes. So classically, you have the generator matrix, which you hit a vector with, and then that gives you a code word. And quantumly, what's the equivalent of this is the encoding Clifford. So you apply the encoding Clifford to some secret, and then that gives you a code word. Classically, there is also the notion of a parity check matrix. And so the parity check matrix tells you, it gives you the syndrome. So the code words classically live in the null space of this parity check matrix, whereas the quantum equivalent of that is like the stabilizer group. So the code states live in the +1 eigenspace of the stabilizer group. So again, the parity check matrix is going to, like when you take the inner product with the potentially corrupted code word, if it gives you 0, then that means that there's no error. And similarly, quantumly, if you measure all the stabilizers on potentially corrupted code state, then it's going to give you like the syndrome 111 if there's no error, but if there's errors, then it's going to be different. So how are we going to use this? So going back to LPN, LPN can be interpreted as a problem of decoding a corrupted code word. So you're given a corrupted code word and you're supposed to output whatever, you're supposed to output X. So we are going to define the learning stabilizers with noise problem, which is the problem of decoding a quantum code word. So the quantum code word here is the encoding Clifford applied onto basically a computational basis state, which is the secret. And then there's going to be some error E that is probabilistic. And here we choose the error to be sampled from the distribution of depolarizing noise. And then the task is, again, to decode, so to output X. So just as a sanity check, LSN includes LPN as a special case. And the way you get LPN from LSN is that you choose the encoding Clifford to be the one that implements matrix multiplication. And E is just sampled from bit flip noise. So like, I guess like for the set of instances of LSN, like that includes all this set of instances of LPN. But LSN is an average case problem. So how are we going to prove the hardness of LSN? So we're going to do a worst to average case reduction. And one way of showing that average case problems are hard is that you reduce from the worst case. So there is a very famous worst to average case reduction that I think was quite a critical piece of the proof in showing that LPN was hard. So this is a reduction due to BLVW18. And given any worst case instance of LPN, they show how to re-randomize the instance. So they show how to make it a random instance. And so if you can do something like that, it means that if you have a solver for the average case, then you can solve the worst case instance. So then it shows that most instances are as hard as the worst case instance. So we are going to try and do a worst to average case reduction for LSN, our problem. So the starting point is, again, a worst case instance of LSN. And this instance comes in the form of a code word which has some errors on it. You know what the code is. And what you want to do is you want to make this a random instance of this problem. So you want to make this like a random code word with a random error and a random secret. So one idea is that we could apply a random unitary to the instance that we are given, and this gives you a random code word. So what sort of random unitary should we apply? Well, if the encoding unitary is a Clifford, which forms a group, then you can re-randomize by just applying a random Clifford. However, this idea fails, actually, because the Cliffords are going to blow up the weight of the error. A random Clifford applied to a low weight error is generically going to make it high weight. And so once you do that, once you apply a random Clifford, then that's going to make the decoding impossible. So the new idea is to somehow play with the unitary so that it's random and yet it's gentle on the error. So it doesn't blow up a low weight error into a high weight error, so that decoding is still possible. And we do manage to do this, but there's a caveat here, which is that we reduce to some average case problem, but it's not the exact average case setting of LSN. So there's still a gap in the worst average case reduction, but that's also true for the worst average case reduction of LPN. So recall again that, so I'm now going to describe how to construct this re-randomizing unitary. Recall again that the input to the LSN problem is an error code word. So what we're going to do is we're going to apply a concept from benchmarking, which is a twirl. And the point of doing this twirl is that it's going to be gentle on the error. It's not going to blow up the weight of the error. So what's a twirl? Well, it's a unitary that consists of a random permutation and followed by a layer of random single qubit Cliffords. And the key point is that because the permutations don't change the weight of the error, and the single qubit Cliffords also don't change the weight of the error. So this kind of like just keeps the weight of the error the same, but it makes the Paulis that are in the error kind of random. So the effect of applying this twirl is that it successfully re-randomizes the encoding Clifford as well as the error. Doesn't blow up the error, so that's good. But we haven't successfully re-randomized the secret. So how do we do that? Well, we're going to just hit with a logical Pauli. And if you pass this logical Pauli through the error and the encoding Clifford, then it just acts as like a set of bit flips on the secret. So now we have also re-randomized the secret. So what is actually the hardness of this LSN problem now that we've done this worst to average case reduction? Well, we study some quantum algorithms to solve the LSN problem in different noise regimes. So for extremely low noise, where the noise rate is, so recall that we consider the error to be from depolarizing noise, and the rate of depolarizing noise is basically the probability with which the depolarizing noise replaces you with the identity. So if the noise is extremely low rate, then it turns out that a very simple algorithm works to solve LSN. Basically, you just project back onto the code space, and this is very efficient because you're just doing Gaussian elimination under the hood. And this is very similar to the situation for LPN, where in the limit of extremely low noise, then you can just take enough samples so that you can determine which are the corrupted ones by majority vote, and then you just solve it by Gaussian elimination. So this just works for extremely low noise. But we also studied a low constant noise regime, where instead the algorithm you would use is not a simple projection, but a pretty good measurement. And here, the runtime then goes up to exponential in k, where k is the length of the secret. So what's a pretty good measurement? Well, it's the optimal measurement to discriminate orthogonal states. And so if there were no error, then just applying a pretty good measurement would actually give you perfect decoding. Because Clifford's take, so like orthogonal states remain orthogonal under application of an encoding Clifford. However, there is an error. So why should pretty good measurements work for us? Well, this is actually not so trivial because we recall that our error was chosen from depolarizing noise, and generically, depolarizing noise can make two orthogonal states contract tremendously, so they can become very non-orthogonal. So there is a saving grace, however, which is that our states are, before the error acted, they were code states. And so the fact that they are code states means that they are encoded in subspaces that are kind of protected under the action of noise. And because of this, the pretty good measurement, which works best on orthogonal states, can still discriminate code states under noise. So the way you would formalize this intuition is to use the quantum Gilbert-Varshamov bound, which says that random stabilizer codes basically have good distance with high probability. And so this means the intuition here is that with high probability, errors do not take orthogonal code words to non-orthogonal code words. So orthogonal code words remain orthogonal under the error, and therefore you can apply the pretty good measurement. And so that's just the proof of how this algorithm works. But this algorithm still runs in exponential time. So could it be that there is a more clever algorithm? This is something that's still to be investigated, but this is the best that we could think of. In fact, we can also kind of prove an upper bound on the complexity class that that contains LSN. And this is really a unitary synthesis problem. So we were able to use some results on unitary synthesis complexity classes. So why is this a unitary synthesis problem? So let me just explain what a unitary synthesis problem is. So it's basically a problem that tells you to synthesize a unitary that transforms some initial state to a target state. And this unitary is in fact guaranteed to exist if you are satisfied with an approximation, with an approximate transform. So there always exists a unitary that does this rotation with the fidelity that is like the fidelity of the states on the pure states on some reduced register which you're interested in applying the unitary on. So we are in the situation where, so LSN is a unitary synthesis problem, and so we show that it's in this unitary complexity class. But so the proof intuition is as follows. So given an LSN instance, recall that for unitary synthesis, you are working with two pure states and you're supposed to rotate one to the other. But an LSN instance is a mixed state because it is a state with some kind of error. So what you do is you purify the noise into a coherent superposition of errors. So this gives you a pure state. And then you just use the NP oracle to solve the syndrome decoding problem to figure out what the error was. And then you synthesize the unitary that decodes and then undoes the encoding Clifford. And this allows you to just solve LSN. So the existence of this unitary is again guaranteed by Ullmann's theorem and the quantum Gilbert-Varshamov bound. So as mentioned, I'm a learning theorist, so I was most interested in what is the application of this for learning theory, because LPN is used in many learning theory lower bounds. And so something that's kind of nice is that we were able to use LSN to prove a statistical to computational gap for a problem that I defined a couple of years ago called learning quantum processes with no input control. So what is a statistical to computational gap? So it's a situation where this problem is statistically solvable. So you can solve it by taking a polynomial number of samples, but yet computationally it's intractable. So what is this problem of learning quantum processes with no input control? Well, so it's a setting where you are given an unknown classical quantum process that maps like classical input to quantum states. And it's kind of like the quantum analog of pack learning, because you are allowed to sample these classical inputs from a distribution. And there is an unknown process that maps every input to a quantum state. And you're allowed to see all these quantum states, and your goal is to figure out what is this unknown process. And so we showed in 2023 that this is statistically tractable at low enough noise rates when the process is some form of noise. But in this work, we showed that this is actually computationally intractable at those noise rates. So this is actually reminiscent of a similar way that sparse LPN is used to prove a statistical to computational gap for the planted-clique problem. And yeah, it would be interesting to come up with more learning theory applications of LSN or similar problems. But the thing is that LSN is actually a decoding problem, not a learning problem, in the sense that you only get one copy of the sample, one sample. And so traditional quantum learning actually needs many copies, many identical copies. And so yeah, so the learning problems to which our assumption applies are those that do not use identical samples. But most quantum learning problems, such as tomography, require identical samples. So I'm now going to conclude. So there are some open questions here, which is that LSN is actually not in microcrypt because it's in this complexity class, which is average unitary BQP to the NP. And if NP is equal to P, then that's just not hard. So is there, but LSN is actually a problem that appears a lot in quantum information because stabilizer codes appear everywhere. So is there some variant of LSN that is both in microcrypt and is also quite natural in quantum information? And there have been a lot of results that have tried to approach this problem, including the previous talk and some of these other results here. So yeah, I think there's a lot of interest in coming up with sort of quantum information, like hardness assumptions that are kind of natural for quantum information. There's also an interesting question, which is whether we can apply the BKW algorithm, which was an algorithm that managed to solve LPN, but still not within exponential, not within polynomial time to LSN. So can a suitable quantum modification of this BKW algorithm break LSN? And finally, our worst to average case reduction is not exact because we are only able to reduce to a definition of average case that is not the same as our definition of average case for LSN. So to improve this worst to average case reduction is really a question about the Clifford group. So if you can think of a very large subgroup of the Cliffords that takes low-weight Paulis to low-weight Paulis because we don't want to blow up the error, then we could potentially improve the worst to average case reduction. So yeah, I think like with that, I conclude my talk.
Thanks. Other questions? Yes, please.
So kind of related to your, I guess, second question.
Yeah.
Do you think you could show that LSN is in this average unitary BQP with an LPN or rather than a...
Oh, so that's a really interesting question. And you might think that we could do so because LPN is, so if you think of LSN without the distribution over instances, then like some of those instances are the LPN instances. However, once you introduce the distribution over instances, it's the distribution over LPN instances does not naturally induce the correct distribution over LSN instances. So there will be a difficulty there in translating the distributions. but it's still possible. I haven't really thought about it. Yeah. Oh.
So the reason that this is broken by an NP oracle, or like you can solve it using an NP oracle, is because the syndrome decoding task is an NP.
That's right.
So I'm not super familiar with this, but looking at it, I know that there are some syndrome decoding tasks which are like sharply hard.
Okay.
If you know about them. And I think they arise for like degenerate codes, which causes problems in other places. Do you think it is feasible to try to base some LSN style variant on those codes where the syndrome decoding is also thought to be pretty hard?
Yeah, I think that would be that's a super interesting prospect. I think if those codes also are as ubiquitous as stabilizer codes, then that would be super interesting. Yeah.
So from the cryptography angle, I guess, what do you believe, right, so it's a quantum analog of LPN. So what do you believe we should be able to get? Maybe like a public key encryption beyond parameters. Like in the classical, for example, there is like a big open question, can we do public key encryption from LPN with more than 1 over square root of n noise? So basically, what are the crypto implications or conjectured crypto implications of this problem?
Oh, I think we were able to get bit commitments, but we weren't able to get anything more than that. But yeah, maybe there's some modification that will allow you to get more complicated things.
But maybe globally, I guess you can always model classical LPN as a special case, you're saying. So basically, whatever we can do for classical LPN, well, it's not completely trivial, but hopefully you can just push it through. Do you feel you might be able to do more? Or
yeah, so I think like the big barrier that we're coming up against here is also what I told Andrew. So this the barrier is really that when you look at the distribution over classical LPN instances, that doesn't translate to the distribution that we have over LSN instances. It would translate to some distribution over LSN instances, but that could turn out to be somewhat of an artificial looking distribution over LSN instances.
Any more questions? Oh, yes.
So if I understand correctly, this was formulated as a search problem. Is there an actual decision version of this problem? And do you expect that to also be hard in similar ranges? Or?
Yeah, there's a natural decision version of this problem. But it's actually, so one way of formulating a decision version of this problem is just to say, like, given either a state that is not an LPN instance, like random, basically drawn from the maximally mixed state, or an LSN instance, decide which is the case. Yeah, I think we tried to prove that this is hard, but we didn't succeed.
Any more questions?
Oh, there's a question there.
Yeah.
Do you get like more crypto than just bit commitments if you assume the decisional version?
Oh, that's a possibility I haven't explored. Yeah, I guess like we couldn't prove that the decisional version is hard, so we didn't go into that step.
Okay. If there are no more questions, let's thank Yihui again. And that is for today. See you all tomorrow.
What?
Oh, really? What?
Yeah.
Oh, really?
Are we still meeting today, or should we just do it tomorrow with Anurag? Well,
No, I didn't.
Yeah, either way, with your stuff.
All right, how are you?
Good, good. Yeah, just
want my pedal.
Sure.
Good.